does that show up in the image? And that's only one pixel that, or one point in the image plane that maps where this XYZ location maps to. So given a real world point with coordinates XYZ, there's only one point on the image plane, U and V, where that point can appear. But the inverse, there's an infinite number of points that are at image coordinates U and V and correspond to real world points X, Y, Z. There's like X1, Y1, Z1, X2, Y2, Z2, many, many points all along the line that would map to this one set of image points. Yeah. Oh, yeah. Okay, thanks for reminding me. So far, we have looked at the transformation in homogeneous coordinates due to rotation and translation. And that's really only the only thing we can do with the camera. It can move the camera around, right? So if the picture changes, then it's because I moved the camera or I rotated the camera. That's what we're assuming at the moment. So we can model rotation and translation, but we don't really have a way to model perspective distortion, which is what happens, or perspective transformation, which is what happens if things are moving further away from the image, from the camera. If they move further away from the image plane, then they become smaller. That effect we haven't really modeled yet. Now, in order to be able to see why that actually happens, we need to know a little bit more about how a camera is built. And the simplest camera model is a pinhole camera model, where we have an image plane where we mount our sensor, which could be a CCD, a charge coupled device, or CMOS sensor. That would be equivalent to the back of our eye, because in the human eye, you have rods and cones that are light sensitive, which is how you can see things. Now, in front of the plane, in front of the image plane, at distance f, there's a lens, and that lens we model as a single point, which is why this camera model is called a pinhole camera model. It's a tiny, tiny point. So any light that hits the image plane has to go through this point. That's how the camera is built. So we see something by having the light reflected from an object, and then that is entering the camera at this pinhole point, and then hitting the light sensor behind. So if I want to draw this, then this is sort of what it would look like. I have a real world object, P1, P2, P3, P4, and I have an image plane in green, and the point that the light enters the camera in front of the image plane, that's called the focal point. Now the distance from the focal point to the image plane is f. Draw that too. So this is our focal point. Yeah. The distance from the image plane to the focal point. So now in order to work out the mathematics, we have to know about similar triangles. And two triangles are similar if the three angles in the triangle are the same. In fact, it's sufficient if two angles are the same, because then the third one must be the same as well, because all three angles have to add up to 180 degrees in a triangle. So if two angles are the same, then all three must be the same. Now, the important part about similar triangles is that the ratio of any two sides, any two corresponding sides, has to be equal. So let's see what that actually means when we're looking at our 3D vision problem at the perspective distortion. Here you can see the drawing. We have our focal point. Now the line that goes from the image plane through the focal point at a 90-degree angle and then just continues forever is called the optical axis of our camera. And here we have a point in the real world, P1, that has coordinates x, y, z, and I'm looking at it with this particular camera, then I need to figure out what are the U and V coordinates. Now, here I basically reduced it to 2 dimensions, so we only have one coordinate here, so just U. And here we have two coordinates, Z, and call this one, I'm not sure if we're looking at the scene sideways, in which case, so in that case we'd be looking at the Y coordinate. So now one thing you will notice is that the sign of the coordinate is swapped. Like here, this line is 0, 0, and this will be positive U, this will be negative U coordinate. But in the real world, this would be negative world coordinates and positive world coordinates. So this point here that has a coordinate of minus 2, that's mapped to some positive U. And P4 that has a positive y coordinate of 2, that will be mapped, the line would go through here, through the focal point, hit P4. So that line would hit the image plane somewhere here, which would be a negative U coordinate. That is actually correct. In cameras, CMOS sensors, the image is flipped around, mirrored, just like it is in the human eye. Now, usually we don't care about the negative coordinate, so we usually just flip them implicitly before we return them. Otherwise, or map them to pixel coordinates, which would all be positive. point. So here we have 2 points, P3 and P1. P1, the light ray goes from P1 through the focal point, strikes the image plane in U1. So the coordinates, the image coordinates of that point will be U1. And P3, which is mapped through the focal point, is hitting the image plane at U2. So the question is, if we know the real world coordinates, so I know X and Z, I know these coordinates of P3, then what is U2? You can also see that this leads, models exactly the effect, or leads to the fact that things that are further away will be smaller in the image. Because the distance from P4 to P1 will be from here to there. The distance from P3 to P2 will be much smaller. And that's what's happening in the human eye, in cameras. That's what the perspective distortion is. Things that are further away in the image will be smaller. So now the question is, how much smaller, or what's the relationship? Now I talked before about similar triangles. So if we look at, let's look at just the one case. If we look at this figure here, then what would be what are the similar triangles in this figure? Those are lines, not triangles. Yeah. But yes, those are part of it. So the first triangle would be from the focal point to along the orange line to the image plane and then down here. Now down here, that's the coordinate that I'm looking for. That's U. So that's the unknown that I'm trying to figure out. What's this distance here from the image plane to the focal point? It's a z-axis, yes, of my world coordinate system that goes through there. Yeah. Yeah. That's f. That's the focal length of the camera. So here we have U, that's that distance F, and I have the orange distance there. So that's one triangle. The second triangle that's similar is that triangle here, right? From the focal point to PZ to P1 and then back to the focal point. So why is that triangles? Why are those two triangles similar? How can you prove that the angles are all the same? Actually, they are complementary angles. They're like two lines crossing, so this angle and this angle, that's the same. So the angle from black to orange is the same as the angle from black to blue because they're complementary. So we have one angle that's the same, and then what other angle is the same? There's a 90-degree angle to the image plane and the x-coordinate axis here. So now we have two angles that are the same, which means the third one must be the same. So those two triangles are similar, but how does that help us? Now the ratio of the two sides must be the same. The ratio of the same sides must be the same. So I can, for example, set up the equation that u divided by f has to be the same as this distance divided by this distance. So what is that distance here? From 0 to P1. That's the x-coordinate of my point. And what's this distance here? From the focal point to PZ. The z-coordinate of the point. So in this case, if my coordinate system starts here, it would actually be easier. Yeah. In this case, it's just the z-coordinate of the point. So u over f has to be the same as x over z in this formulation. So then I can take that and simply expand the formula in order to. What happened to you? So UP over F is equal to, and since one of them is negative, it's negative XP over ZP, where XP and ZP are the X and Z coordinate So then I can rewrite that as UP is equal to negative XP multiplied by 1 over ZP multiplied by F, or on 1 over negative XP times F divided by Z. So now we have our equation, but, and I could calculate this now, but we have this whole framework that we put up for our coordinates using matrices. Now, how could I represent this particular setup as a matrix, this particular equation? Because matrices are, in a sense, very nice, right? Because we have 4 by 4, I can compound them, I can do translate, translate, rotate, rotate, translate, rotate, translate, rotate. I can combine a whole bunch of them, keep left multiplying them, multiply them all together, and end up with another 4 by 4 matrix. That will be the exact transformation from whatever I did before to whatever the end, the compound translation or transformation is supposed to be. So this is very nice. But now the perspective distortion we cannot really represent as a matrix transformation like that. There's no way, because in one it expects both xp and zp as variables. Like it includes both of those terms. Um, but the last class I already said that using homogeneous coordinates, there's a very clever trick in which we can overload the meaning of homogeneous coordinates to come up with a more general representation of coordinates, which allows us to then include perspective distortion as just another transformation. So this is really cool. One, we can add a scaling for affine transformations, right? So if I have a matrix Sx, Sy, Sz, and 1, then here this would map to just the 1, but Sz would scale the z coordinate, the y coordinate, and the x coordinate respectively. So for homogeneous coordinates, we extend our 3D coordinates, x, y, xi, yi, zi, to a more general term, which is kxi, kyi, kzi, and then k. So now, any point in 3D space can be mapped to an infinite set of points in homogeneous coordinates, basically representing a line in the 4D space. And using, but the special trick is that our coordinates now have this extra factor attached. So now I can attach an extra factor. Instead of just having 1 here, I can also have 2 or -3. And that factor is what's going to be divided by kzi afterwards. So using this representation, I can now this code is not responding. this?
Yeah, yeah, and it's not the same with the course now.
It's not the same with the course, of course.
Means the spelling. It's not the same.
Yeah, it just has my face in it.
But the lecture is like not the same.
I'm sure. Oh, this one is just mirrored. But if you look at it on the Discord, it will be the right way. Like,
The slide, the page is not the same.
really? How did that? That is strange. Oh, the driver may be killed or something. Okay. Okay, now it moves again. Yeah. Okay. funny problem. Okay, so we have the homogeneous coordinates for our point PI. We now extend the representation, and in the representation here, I have to multiply it by minus my x coordinate multiplied by f, so that will be minus f, and then I have to divide it by z. And that's something that I cannot do in a standard sort of matrix representation. But using homogeneous coordinates, I can generate the perspective distortion matrix, because now I have minus f times xi, which is what will be calculated at the top row, and the z coordinate, I will divide it by the z coordinate, which is this coordinate here, like 0, 0, 1 multiplied by zi. And so then that gives me minus f multiplied by xi divided by zi when I take the output of this, the left-hand side of this, which is in homogeneous coordinates, and convert it into 3D coordinates. Now, one trick that you see sometimes when you read the research papers, I said that there's this inversion of coordinates, like u1 is positive, but the x coordinate in the real world is negative. And that's sort of not so nice. There's a trick to deal with this. Instead of dealing with the focal plane, the way the camera is physically built, right? The image plane is behind the pinhole. That's how the physical constructs. But logically, I can sort of think of a virtual image plane in front of the focal length. And then the equations all remain the same. I still have two similar triangles. The ratios still have to be the same. Except now, if an x coordinate is positive, it will be a positive in the image plane. And if it's negative, then it will be negative in the image plane. Right? Because any point that comes through here will be above the 0 line, so it would have to be positive. Whereas if I project it to where the real image plane is, it'll be the same coordinate, it'll be this u2, it'll be the same, but it'll be inverted, it'll be negative. So sometimes when you see people research articles or about computer vision or cameras or camera calibration or photography or something like that, then sometimes they draw the camera with the focal point behind the image plane, which physically doesn't make sense, but logically it makes sense. So now you know why Some people prefer it this way. Other people don't care, and then they just deal with the inversion of the coordinate. So this will change if we pretend that our image plane is in front of the pinhole rather the focal point rather than behind it. So now instead of having the minus f here, I can also take the matrix and divide it by f, all the values. And in fact, negative 1 over f, then I end up with this transformation. And the points are not still inverted. So in theory, this then allows me to model the scene. So what I could do is I can start with my mobile phone, and now I have a camera, right? And now I point it at a scene, and if you just get up and move the chair, please, and put it down. Right, now I want to know how far away am I from the chair. Because I need to drive there, and the robot is tired, needs to sit down or something. Right? So we have now all the math in order to be able to represent that problem. Because let's say my you have another phone. Turn on your camera, please. And you come here and just hold it like this. So this is the camera. This is the object that I want to see. The scene that I want to interpret, right? So now I can say, okay, my coordinate system here is 0, 0, right here. Here is 0, 0. Then, in order to model what happens with to calibrate the camera, I can then just take the camera, and the only thing I can do is translate it XYZ direction, right? Or rotate it. So then I can say, oh, to go from here, then move to here, then move to here, move to there, and eventually I need to tilt it, right? And then this will be the position of the camera. So I would need to measure the rotations and the translations, and then the perspective distortion at the end, in order to, and then I can take any 3D point, XYZ coordinate, and I can tell you exactly where that will be in the image. Okay? So now, the question is, if I now give each and every one of you that particular task, right? And I say 0, 0 is here, exactly this point on the floor, then calibrate the camera. Then you can pick up the camera, you can say I move it there, and then I adjust the angles. So there will be like a translation, then there will be a rotation matrix for pitch, yaw, and roll, and then the perspective distortion. Now, to calculate the perspective distortion, we need to know one parameter. Which parameter? What do I need to know? We don't have all the information yet to be able to do that. No. I need to know F, right? Right now we don't know what the focal length of the camera is. Now, for most cameras, if you, actually you can check. This is a Zenfone 6. Just check on Zenfone 6 and see if it tells you what the focal length is. For a lot of cameras, they actually do that. Certainly professional cameras, that's true. Also, this particular phone has a zoom function. So that means I can change the focal length. See if it says something. Just search for focal length. Focus. F is FO 1.8, 26. Yeah, 11 millimeter equivalent focal length. Yeah. So you can get that out of a data sheet. But now, if I ask all of you to measure that distance, and especially these angles, then I have, what, 5 students here. I will get 5 different answers, right? Most likely. 6 students here, I'll get 6 different answers. So the problem is that's actually not so easy. Even though the position, if you stand here, right, not exactly on the grid line, then the position is already not so easy to measure. You have to drop a weight down to see where it balances in order to get the x and y coordinate of the camera. Then you need to check the height. And the angles are even harder. How would you measure the angle? And if your camera is there, it's not too bad. If your camera is, if you want to model this projector, right, then it will be much harder. You have to climb on the table and try and measure these angles. Now, if you can do that, or with what we talk about afterwards, you can do some very cool things. Okay, I think enough of the. I'm not sure if I showed you this video already. Yeah, let's watch this one. So this is called projection mapping. So you can have some very cool effects. And for some reason, they turned out to be very popular with car shows. Um, so I think this one is from BMW. So this is all controlled by multiple projectors that basically turn on highly focused beam. But it looks very amazing. Like visually, it's very cool. In order to be able to do that projection, you need to know what pixel you need to turn on in order to turn on that part on the car, which is sort of the inverse of the vision problem. So this is just a very high-powered projector drawing an image at the car in the right geometry. The scene will look totally different when you project it on a screen. It only works on that particular car if that car is in the right position. If you move the car, then everything is wrong already. So they really went to town on this one. So if you want to do that with a projector like that, you need to know the exact displacement from the car to the projector and the focal length of the projector, and then you could do that. However, the problem is measuring these distances and angles is very error prone. It's not very easy. So what can we do? How could we solve our dilemma? Well, one thing we know is that our camera transformation can be modeled as rotation followed by translation followed by perspective distortion. I could have a sequence of those, right? If I really don't like it to do it in one shot, all the translations, I could break it down into smaller. But at the end of the day, whatever I do, given that particular um, framework that we established, I end up with a 4 by 4 transformation matrix. So in order to be able to do this mapping, all I need is this 4 by 4 matrix, which means I need to know these 16 numbers. If I know these 16 numbers, then I don't care about what the yaw angle is or the swing angle. I can calculate all of that later if I want to. But for the projection, the only thing I need is the correct 16 numbers there. Now, the z coordinate, row number 3, if I now think about this translation here, then row number 3 is actually not important. Right? Because it's calculating the z coordinate of the image plane. The z coordinate of the image plane is always going to be 0. Because it's a plane, right? So the third row doesn't really give us any information that is useful. It'll just map everything to 0. So if I wanted to achieve that, I can just set A31, A32, A33, A34 all to 0, guaranteed it's going to map to the correct Z coordinate. So it's actually a little bit easier. I only need 12 numbers, not really 16 numbers. Because the ones for the third row are not important, are not useful. So, okay. So now let's say that I am given, I take an image And ideally, you want to take an image with good geometry. So here I took an image of the Rubik's Cube. Right? Now, the Rubik's Cube is a very fixed geometry. So if each one of these squares is 5 millimeters, then, and I set the origin here, and I say x, this is the x plane, this is y, this is the z plane. If I just establish a world coordinate system on that particular cube, then if this is 5 millimeters for the whole square, then this would be x is 2.5, z is 2.5, and y is 0. And this would be 7.5, 2.5, and 0. 7.5, 0, 2.5. Z coordinate would be 2.5 for all of these. So I can actually look at the image and click on the point and say, this is the center of that square. Right? So I know what the pixel coordinates are. So I can say the pixel coordinate here for the blue one is 256 to 100. Let's take the green one. 264, 460. And the real world coordinates have to be the size of the square divided by 2, 0, size of the square divided by 2. Now, the size of the square I can measure a lot easier than the position of the projector. That I can do easily by just using a measuring tape. And so then I can get a set of image coordinates, u and v, and the corresponding real world coordinates. So I assume that I have that. So I have real world coordinate x1, y1, z1. In the image is at u1, v1. And real world coordinate x2, y2, z2 is at image coordinates u2, v2. Okay? So now I have take a set of these points, maybe not all of them, but maybe just the bottom 2 rows. Something like that. So for each point now, I can expand the equation that I get. And in particular, I have to first calculate on the right hand side here, I will have xi, yi, zi, 1, because it needs to be in homogeneous coordinates. So I need to have 4 rows here. I have 4 columns. So for the matrix multiplication to be defined, I need to have 4 rows here. So this will be xi, yi, zi, 1. And then I get my pixel coordinates ui, and the first row here, this will be ui. The second row will be vi. The third row will be 0. And this one, this bottom row here, will be our denominator, the one that we divide through. So if I write this out, then for each point now, I get two equations. I get a11 multiplied by xi, a12 multiplied by yi, a13 zi plus a14, which is the bottom part, the top part of that equation, and then I divide it by the bottom row here. A41 xi, A42 yi, A43 zi, A44. And similarly for vi. That establishes the equations, the mapping from real world coordinate. On the right hand side here, I only have real world coordinates, xi, yi, zi, and on the left hand side, I have image coordinates, ui and vi. So now I can expand this. I can reformulate this so that I can take ui and I can now before when we're dealing with this, our unknowns would be ui, vi, xi, yi, zi. And then one set is known, the other one you're trying to calculate. But in this scenario now, when we're dealing about with the matrix, when we're doing camera calibration, I actually know what ui and vi is. I don't need to calculate what ui and vi is because that's simply the position of the feature in the image. So I can read this off here, right? 245, 461. Bam. That's ui and vi. So I know what ui and vi is. That is known. What is not known, what are the unknowns, is A11, A12, A13, the 12 A's, in order to form my 4x4 matrix. So ui and vi are known. A41, 42, 43, 44, 21, 22, 23, 24 are not known, and also A11, 12, 13, 14. So I have 12 unknowns here. So I can multiply the equation through by ui. So now I just took the denominator, multiplied by ui and vi respectively, and then I bring everything over onto the left hand side. So what kind of equation is this? Well, I have unknowns, but xi, yi, xi, 1 here, ui, xi, yi, ui, zi, ui are all knowns. So the unknowns are only multiplied, which means it's a linear system of equations. Right? I'm given a linear system of equations here. So that means for every point that I get, I now get two equations. The first one is for ui, the second one is for vi. So every point gives me two equations. And I can now set up a system of linear equations where I have the unknowns, A11, A12, up to A44, the 12 unknowns, with the factors that I need to multiply. Now, the UI one will be the first row here. So it will be xi, yi, zi there, actually not. Yeah, minus 842 yi minus 843 z I. Yeah, that's correct. So I get two equations for every point. First one will be xi, y, zi, xi, y, z, 1, negative x, ui, negative y, ui, so on and so forth. Now all of these in the left-hand side here, all these numbers are known. That's how we get out our system of linear equations. Now, in order to solve that system of linear equations, how many points do I need? So now I have a system with 12 unknowns. How many equations do you usually need in order to solve a system with 12 unknowns? 12, yes. So I need 12 equations, but each point gives me two equations, right? Each point, here I have one point, I get two equations from that one point. One for the mapping of u, one for the mapping of v. So that means if I have 6 points, I get 12 equations, which should be enough to solve that system of linear equations. So you need to have a minimum of 6 points. There's some constraints, right? The points cannot be linearly dependent all on each other. So if all the points are in a straight line, it wouldn't work. But as long as your points are distributed over the image, that's fine. So that's how we can then calibrate the transformation, the compound transformation matrix. In that case, this is much easier, right? Often, most situations, this is a lot easier because instead of having to measure the distance between the car and the projector, I simply need to take a picture of the car from the projector, right? And then I simply need to click on where the individual features are and read off the x and y coordinates. So pretty neat, pretty cool. If I do that for 6 points, in theory that's enough. Right? Definitely I cannot do it if I have less than 6 points. If, however, in practice, a rule of thumb is that you need to have at least 15 points to come up with a good camera calibration. So in that case, we actually have then too many points, and we need to solve the pseudo-inverse model in order to find the least squared error approximation. So because every time I click on something in the image, I may make a mistake. I click a little bit too high, a little bit too far right, too far left. So instead of just looking at the 6 points that I selected, I can do that for 15 points. Each one of them is distorted by some noise, but if that noise is if it's noise, which means it has zero mean and is normally distributed, then, okay, then I can get the best approximation that I can possibly get given the data that I was given. So we can usually, if you do this in practice, use not just 6 points, but you use about 15 points. And then you get a very good solution for your transformation. Now, one thing that we have here is our right-hand side is 0. If I just multiply out all the equations, I end up with the right-hand side being 0. So of course, then the solution, one solution would be to just set A11, A12, A13, everything is 0. But the null solution is not the one that we're interested in this case. So we want to find the null space of this particular equation, system of linear equations. So this is a homogeneous system of linear equations. So the right side of it is 0. So it's not a multiplied by x is equal to b, which is the way that a system of linear equations is usually written, but it's a multiplied by x is equal to 0. So there's a trivial solution where I simply set everything to, this is actually called the trivial solution, where I set everything to 0, but that is not the one that we're interested in. Right? We want to find if there's a non-zero solution, if there's a null space. Now, any solution that I find, I can multiply all the values by some constant, it'll still be a solution. So that particular solution is not unique. What we want to do is we want to find the solution where the lengths of the vector, we just normalize it to 1. Because I can scale the solution any way I want. Now the algorithm for doing that is the linear distance transform. We have 6 points. Each one of the points gives us 2 equations. If we have more points, then we think it should be better. But in that case, we have an over-constrained system, too many equations. So what we want to solve is the least squared error approximation. And this is actually the Penrose-Moore pseudo-inverse method is the way to do that. It is very cool in a sense because you take your original system of linear equations, ax is equal to b, and you pre-multiply both of them by the A transpose. And then you can see how that actually gives you the square of the errors when you go through in detail. And then the solution to this system of linear equation will be the least squared error approximation for the over-constrained original system. So all you have to do is pre-multiply both the right side and the left side by AT, and now you have the least squared error approximation, which is very cool, very easy, very good trick to remember. Now to solve this system of this homogeneous system of linear equations, we can use the singular value decomposition, because what we actually need to find is we need to find the vector that corresponds to the smallest eigenvalue. Because here, what I need to solve is ATA multiplied by x, and this is what the singular value decomposition already calculated. So now, just a very simple, quick reminder of the singular value decomposition, or a very simple introduction. Using SVD, we can take a matrix M and decompose it into a product of 3 matrices, so that it's U multiplied by sigma multiplied by VT, where U is a unitary matrix of eigenvectors for the matrix MMT. Sigma is the diagonal matrix, so it's a matrix that's 0 except on the diagonal rows. Those are the square root of the eigenvalues. And the eigenvalues of MTM or MMT, doesn't matter, the eigenvalues would be the same. And V is the unitary matrix of eigenvectors for MTM. So I want to find the solution with the smallest eigenvalue in MTM. Now, singular value decomposition arranges the eigenvalues in such a way, sorry, not the eigenvalues, the singular values, which are, it's the square root of the eigenvalue. So those values are arranged by largest to smallest. So I want to take the one with the smallest eigenvalue, which has the smallest singular value, which means it will be the last row in the last column in VT and the last row of V. So then V will be 12 numbers. Those are the 12 numbers that I want to plug into my compound transformation matrix. So we can change, we can implement that in Python. So I can define a function, calibrate camera, where I'm given an image and a set of points, and then here I have a Boolean to specify whether I want to normalize the points or not. So then for each point, which has UC, VC, X, Y, and Z, I calculate the position of the image coordinates, and I assume that they're at the center. So what is UC? From the point. So when we look at this particular picture here, then I assume that the coordinates that I get are the 0 would be at the center of the image, right, in the middle of the image. But when I click on things, when I click on points in the image, I don't actually get the center. I get 245, 461, where 0, 0 is on the top left. That's the usual coordinate system for an image. Right? We assume that this is pixel 0, 0, 0, 1, 0, 2, 1, 0, 2, 0, 3, 0, 4, 0. But given the geometry, the coordinates that we actually wanted to apply should be that 0, 0 is in the center of the image. Right? In fact, it should be the center of our image plane. So I want to take the coordinates and I want to map them from U image coordinates to U camera sensor coordinates. And that would be a normalization step. So if I want to normalize, then the height of the image is I height, the width of the image is I width. So the center would be I height divided by 2, and in the y direction, and in the x direction this would be I width divided by 2. And then I want to calculate new coordinates u and v. Otherwise I just pass in the original coordinates. I set both of them to 0. So then I construct my A matrix. So x, y, z, 1, 0, 0, 0, negative x, from exactly this equation here. That's just the Python code to generate this A matrix. So here's the first row, here's the second row, both of them I append to A. Then I convert it to a NumPy array and calculate the singular value decomposition. Now the singular value decomposition I now know should be the last vector, so vt minus 1, it should be the last row in vt, the last column in v. And then I've changed that. It's now a vector of 12 numbers. Now I map it to a 3 by 4 matrix so that I have it in matrix form. And then this will be the solution that I want to return. So given my matrix A, then I can write a function which takes A and a real world coordinate x, y, z, and then calculates where that should be in the image. So this maps this function here maps from real world coordinates to image coordinates. And then I take the points on the cube and I simply plot them to make sure to see how much error I get, or what the error is. Oh, so here are the points that I extracted from that particular image. And here's the output. As you can see, just given the points that I used, which were all on the front face of the image, those are the points that I actually used for my calibration. Even then, I get a pretty good calibration already. Now, there's a lot of error on the top here. Why is that? Or what's the problem there also on the right hand side? That problem is really due to the fact that I didn't disperse the points very well over the image. Right? I don't have any information. I didn't take any points on the top here on the back. So there's still quite a bit of noise there. If I choose my points more carefully on all parts of the image, then this will work a lot better. So if I want to improve that result, that's easily done. I just need to take more points uh, over the entire image. Usually you want to have a minimum of 15 points. And if your coordinates, if you scale them all to be mean 0 and variance square root 2, then the system, the numerical stability of the SVD algorithm is better too. So we can do those things. So here I added some more points. Same points as before, but I added some more. Let's plot. Now you can see the result is much better just by taking the points, a couple more points, and distributing them more over the entire. Actually, let me see what happens if we only take 6 points. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. So let's just take. So this now is really bad, right? I only have these 3 points and these 3 points. So it's a very bad selection of points. Yeah, see here the cube is even more skewed than before, using only those 6 points. Because I don't have any information about that part. But if I add more points, then we get a really nice camera calibration for this. And now I can read off the distance from the camera to the origin, for example, right? Because that would be in my A matrix. Now, one of the problems that we have is that we get the focal length, and that should be negative minus 1 over f. That one, however, is distorted by the scaling. So you don't really get the same focal length as you would get out of the data sheet. However, that doesn't really matter, right? As long as the matrix maps correctly, usually we don't care what the focal length is. As long as my real world coordinates are mapped to my image coordinates correctly, or the inverse, the mapping is correct, then that's good enough. But this would be the matrix that I got. Also, you see this should really be 0, 0 here. 1, negative 1 over f 0. That's also not quite true. The the system usually works better though to be able to compensate for some noise with those numbers as well. So usually we just leave them like that. And because you don't have to detect what the focal length is. So now you can copy this notebook and either take the same image or take another image with a regular 3D object. Now, one of the things is using this particular approach only, we cannot really calibrate on a plane only. So the points, I need to have the points in 3D space to get a good calibration. If I only have have them in um, 2D in a plane only, then the calibration won't be that accurate, yeah, because then there's infinite number of solutions that could happen. So it's better to have a 3D object that is regular. So what you can do is, let's try that. Okay, so what you can do is take a picture of a building like this, for example, and then we can assume, just make an assumption that the the width of the windows is 2 meters, and then see if you can calibrate this particular building here. If you can do that, then you can figure out how far away this point is from the actual building. Now, I would need to know exactly the size of the windows to get the distance exact, but for now we just guess what it is so that we don't need to find out the blueprints of the particular hotel. Okay. So find a picture of anything really, buildings are good, Rubik's cubes are good, and try and calibrate that using the code from the camera calibration um, workbook, Jupyter Notebook. Okay. So copy that and start working on that. If you are more difficult, it will be to take a picture of a car and then look at the blueprint of the car, where the different points are on the car, and then calibrate that. That will allow you to measure the distance to the car. Or it would allow you to do the projection mapping to the car. Because once you have that A matrix, that's all you need in order to be able to do the fancy light show. Or you can do type A 101, or what else would that for regular structure? Regular structure is just so that it's easy to get the 3D points. Or you can try a street view too, if the street lights are in the same position. And here, this kind of picture would not be good because all the windows are in one plane. They're all only one part of the building. You need to be able to see both parts of the building, two walls of the building. Yeah, that will be good. Still waiting for the okay. Yeah. Actually, yeah, it's better if you get the. I'm not sure if this works on PC. You have to pick the direct link, I think. Yeah. If you want to use the post image, then you need to give it this URL because this one will be to the post image website. This one will be directly to the image. So anything regular, a tree of course is very hard, right? Tree is almost impossible to do because you don't know where your leaves are. It has to be something man-made. Uh, yeah, this would work, except it's artificial image. It will be more fun to do it with the real image. But close enough. Yeah, that's the image. Okay, this one's pretty easy. Go to the Actually, to do the car is not so easy. Just thought about it because none of these are really flat surfaces. They're all round, like modern cars all have a very rounded shape. Have to look for old American muscle car or Mustang. That will be better.
Maybe Mercedes
Mercedes, maybe.
or G-Class. I think it is. Yeah.
G? I didn't even
Yeah.
know there is a. Oh yeah, this one is more boxy. Yes, that one will be better. Yeah, you can try that one if you can find a blueprint. Oh, who lives here?
As a developer, I realized ClickUp is an incredibly powerful engineering tool. I wish I was humans are pretty incredible. We've made great.
I'll just assume that this is a cylinder, and we'll see how it goes. This is pretty ambitious. So, since I assume this is a cylinder, I put the XY center into the center of the circles, and the Z coordinate going upwards. So then I need to first figure out what that angle is that is actually leaning, that the tower is actually leaning in this particular picture. Looks like this wall is straight, this wall is straight. So now I need to have let me see. There's a desktop mode. Can I change the language here somewhere to English? Spell check. See if there's settings. No, no, these are all the different. Ah, yeah. Of configuration here. Wow, really no way. Well, you have a voice plug-in. Here, English. Okay, good. Now I have it in English. Okay. Now, picture. No. your pictures of it? Okay, yeah. Think about the dimensions and the real world coordinates of the objects that you can see. Yeah, that picture is good. Now maybe a little bit because the right hand is good, but on the left side you don't have so many windows. But you can estimate it also. It may work. You can just try it if it doesn't work. Okay. So Now I can read, finally I have a program I can use to read the coordinates of my image. Uh, so here I can select x and y coordinates. So let's have a look at Wikipedia for Tower of Pisa. 55 meters diameter, 15.484 meters, 3.97 degrees. Okay. So then we can simulate that. So the diameter for 15.484. Now this is going to be a rough approximation, so the 484 doesn't matter, but since we have it, then we have the lean angle, 3.97 degrees, and the height, it says was 58, 55.863. 55.863. So that gives me that. So now I want to pick real world coordinates. So I'll take 3 points, the center, the left, the center, and the right. Each one of those three, or one, two, three, 6, 6, 7. So the height of a floor, oh, there's the variable stuff. Height is 55, 3, so Pisa tower height is this. The diameter is 1544 divided by 180 multiplied by mass of pi to convert it to radians. So the height of the floor would be the full height divided by 7, because there seem to be 7 floors there. Let's check please. Right? And now, so I assume they're all the same height. Obviously, it's not quite right, but we have 1 floor, 2, 3, 4, 5, 6, 7 floors. So the height is this divided by 7. And then the coordinates of the points that I'm interested in, I first put them in the coordinates of the building and then map them to real world coordinates. So 0, 0 is the center of the building. So if I have x going this way, y towards me, and z going upward, x, y, z, x going to the right, y going backwards, and z going upward, which gives me a right-handed coordinate system that we are familiar with. Then the points that I have would be floor. Well, z coordinate would be floor multiplied by the height of the floor. And for each one of those, I want to take the point on the, cannot take a point on the very left. Oh no, it's okay. It should be able to see that. So then the x coordinate would be minus p diameter, y coordinate 0, and floor times the height of the floor. Then the next one would be 0, p diameter divided by 2, p diameter divided by 2, and next one would be PDM positive, PDM divided by 2, 0, and floor times height of the floor. So now for each floor I can get 3 points, one that's right in the center, one at the very left edge, one on the very right edge. If I do that for 3 or 4 floors, then I have 9 or 12 points, which should be sufficient to calibrate the camera. But now the problem is the coordinates are off because the tower is tilted to the right. So how can I fix that? Well, I could solve the geometric problem. I can say, here's my tower, first floor, second floor, third floor. Now it's tilted by angle alpha. So what will be the new x and y coordinates? X, y, z coordinates of that hill. Um, and I have 3 points for each one of the floors, like this point, this point, this. Now I also know this distance because that would be the diameter divided by 2, or the radius of the tower. So, okay, then these points here, they're coordinate because the tower is rotated, will move down. Will move down by that distance, which will be, so if this is alpha, this is also alpha, right? So that means that will be shifted by sine times alpha. Sine alpha multiplied by the diameter divided by 2. These ones correspondingly will be shifted upwards, right? But that's not quite right because we rotate it around here. shift this one, then that's not quite correct. First, I need to shift that one point, this point, and then this point, and then apply that correction. Any other way in which we can solve this?
And maybe we can use the forward coordinate.
Yeah, we could do that, but then what we would be doing is basically redoing all the work that we did already for our homogeneous transformation, right? If I use the polar coordinates and then solve the system, solve the geometric problem, and then I convert it back into Cartesian coordinates, then I actually end up again with what kind of transformation? Then I again end up with a 4 by 4 homogeneous affine transformation, right?
Yeah.
And in fact, we already know how to model this because the coordinates that I said was this is x, this is y going backwards, and z is going upwards, right? So that I have x, y, z, I have a right-handed coordinate system. So now, if I rotate around y at this point here, that's exactly what I want to do. I need to take the whole tower and rotate it around this point, but that point would be the y-axis. So now the only question is it plus 3.97 degrees or negative 3.97 degrees, right? So um, if we rotate around y, that means x, y, z. I'm looking at y, down y towards the origin. And I'm rotating counterclockwise. If I do x, y, z, then we're rotating counterclockwise. So x, the tower is like this, x, y, z, and I rotate counterclockwise, then it will be going this way, which is the rotation that I want. So it should be plus 3.97 degrees. So I want the rotation matrix to rotate around either angle, and the coordinates that I have, let's just, the coordinates of the tower I'm going to put in U and V later on, but right now, I just leave that at 0 because I need to read those off the image. So I'll do that later. I just want to make sure the rotation is correct. So the first point would be exactly this. Put that at 0 for the height of the floor. And then the next one would be this one. Uh, 0. That will also be negative. 0, 0 plus 4. And the next one is 0, 0. And 0. What 0, 0, 0. 0. Plus 2. Z. X. 1. Z. X. Y. Z. So this is on the first floor. Second floor. So now I just want to check about my coordinates. Converting to immediate coordinates, and then just print them out. So let's just rotate them by 0 degrees first. 4. It's again a homogeneous coordinate. So we have x, -7, -7, 7, 4, 0, 0. Okay, now we change the angle. So we get -7, 0.53, then we rotate 7.73. So that tilts the tower in the correct direction, because the one on the left is going up, z-axis is increasing, and here the z-axis is decreasing from the right-hand side. But if you look at the image, these points here on the left-hand side, they go up. On the left-hand side of the image, on the right-hand side of the tower, if you want to, these points here move up, these points here move down. And that extends with the tilt of the angle. So here it's -0.53, and then it goes to 8.49, 7.96, 7.42, 16, 15, 15, 30. So there it goes down. And all the points are shifting towards the right. So that would be that. Now I want to be able to read those off. So this will be floor 0. So first point will be 254, 484. 254, and this is how I can start. 252, 483, 52, 483. Next point will be the center point here, which should be here. 316, 489. 489, and the next point here, on the right hand side, 391, 500. And these will be the coordinates correctly. the points. So the points that I want to add is U, V, X, E, Y, B, Z, X. Everything else will be exactly like. So you can try that if you haven't done your own picture yet. I'm just going to have a walk around, see how far you got. Otherwise, complete it as a homework until next class.
Sir,
Yeah.
what's the website that you read the information?
Oh, it's called iView. Um, it's not a website, it's actually just an HTML file you can download. Then you can run it in a browser. So this website here, I'll post it on the yeah, it used to be every program used to display the coordinates. GIMP certainly does it, but I uploaded Krita, which is also very nice, but it didn't show the coordinates. But I seem to remember that it did that. I don't know what happened to it. So then you can either use it online or you can just download it to the computer and save it there. So when we update, did you calibrate it? Okay. Then make sure you do that until next class so that you know how to use the routines, or you can